exactly. Great. So does anyone want to try to tell me where the fault is? I have a laser pointer you can use. There's a hand over here. Do you still want to? Your hand went down. Okay. It's that button. Yeah, so that is a good guess. Based on what we learned on the field trip, right, there's a flat region, and then this line demarks sort of the beginning of the hills. So based on what we learned on the field trip, that's a very good guess. For this particular fault, that's not exactly where it is. Do you want to redo it? Okay, yeah, take two. Yeah, there we go. Why do you say it's right there? You can see sort of a canyon. All of the other sort of canyons, all of the other valleys in this hill system, they sort of bend, they go their own way, they're not super long, but there's one really long canyon that runs straight up those mountains. And yeah, that's correct. So this is an inset that's right here, shown by these black lines, which are really hard to see with this projector. And this red line is the San Andreas Fault. It runs right up, sort of slices these mountains in two, and creates a big, long, linear valley in between the two of them. Great. Okay, so we've zoomed out a bit. Oh, I have the fault already marked. No one else gets to use the laser pointer. This is the fault, obviously, the San Andreas Fault. So now you can see that as we're pushing farther north, it's really fairly flat on one side and fairly hilly on the other. This orange line is the Hayward Fault. This is the Calaveras Fault, this little red bit that transitions to the Green Valley Fault on the other side. Right, so what is one of the things we've noticed is flat area on the right and hilly area on the left. What's another interesting feature that you can see? It's really hard to see with this projector, but something along the fault that might identify a fault being there. What else do you see? Right along the fault, that you don't really see anywhere else. Water. Yeah, there are two lakes, in fact. There's a lake here, and there's a lake there. And they are elongated. The fault runs right through the middle of them, and the two lakes are elongated in the direction of the fault. So this is called Crystal Springs Reservoir. This is Interstate 280, right? I don't go to this side of the bay much. I think this is Interstate 280 that runs along Crystal Springs Reservoir. And a little bit farther to the north, there's the San Andreas Lake. The fault runs right underneath San Andreas Lake. Yeah, I believe that San Andreas Lake had its name before the fault did, and the fault is named after the lake because the fault runs right through it. But I'm not 100% sure of that. It's not terribly important, but an interesting bit of information that I don't know which way is forwards and which way is backwards. All right, so we have two elongated lakes along the fault. Yeah. Yes. So just having so the question was, because the Hayward Fault is a lateral moving, i.e. strike-slip fault, does that mean that the San Andreas is also a strike-slip fault? The answer is that, in this case, yes. If you have two faults that are really close together, it doesn't necessarily mean that they are of the same orientation. But in this case, in California, for the most part, yes. If you have two faults that are close together, they're going to have similar movement across them. Okay, so let's zoom northward a bit. So this is San Francisco, the peninsula. This is Treasure Island and Yerba Buena Island. And this is the bridge that goes across to Oakland. This is the Golden Gate, and the fault runs out into the ocean, and it comes back on the ocean. And the fault was in the last picture, so hopefully people know where the fault is, but I want to give another chance to use my laser pointer. Someone back here want to use my laser pointer to tell me where the fault is? Laser pointers are a lot of fun. Yeah, you do. Okay, good. It's the button closer to the end. Yeah, exactly. Why do you say it's that? Uh-huh. Yeah, it does. It looks like Point Reyes is separated. If you had to choose a single linear feature in the entire map, not knowing where a fault was or anything, it would probably be this sort of odd-looking straight line that appears to almost slice this piece of land off from the mainland part of California. So yes, that's correct. The San Andreas Fault runs right through here. Bolinas Bay is more or less created by the fault, and Tomales Bay is more or less created by the fault also. If you go to Point Reyes, they have an earthquake walk, which is, in my opinion, kind of underwhelming, actually. They have like a bunch of posts that are supposedly marking where the land was in 1906, or how much it moved in 1906, but the posts are obviously brand new, which is kind of unfortunate. Anyway, yes, so this is the location of the San Andreas Fault. It pretty much slices off this piece of land, and that's part of the Pacific Plate. Another interesting thing is that this bit of land is moving northward, right? If you think about it, this piece of land is moving toward Alaska, while this piece of land is not. So if we wait long enough, who knows? Another interesting little piece of information, in the 1960s, I think it was the 60s or 70s, there's a lot of expansion going on in the Bay Area. Lots of people are moving here. We need electricity. And the 70s are when people were really into nuclear power, right? So they thought about building a nuclear power plant here. So what do you think of that? Yeah, they decided not to, which is probably a good call. There's like this little spit of land that sort of, I can't imagine like a worse place to build it. Anyway, okay, let's zoom out a bit. So again, so this is San Pablo Bay. We're down about right here. San Andreas, what's the city called? San Francisco is down here. This is Point Reyes, and this is the San Andreas Fault. It runs up and sort of bounces on and off and on and offshore and extends out into the Pacific Ocean up here. Zooming way out, we've got California. So this is the Bay Area. We're looking pretty much at northern California. The Sierras are this big lump of green, dark green on this side of the state. And the San Andreas Fault looks about like this. This is not a Google Earth. This is me trying to draw dotted lines in PowerPoint, so that's not exactly where the fault is. Don't use that to guide whether or not you build your house out here, because that may or may not be where the fault is. But more or less, this is where the San Andreas Fault runs. It's interesting that I have it stopping here, right? No one ever hears about the San Andreas Fault in Oregon. So where does it go? Where does the San Andreas Fault go? What happens to it? Can a fault just stop? That's a weird thought, right? What happens? Yeah, there's a new plate. So we will learn about this next week. I think we're talking about plate tectonics pretty shortly. There's another fault here. It's called the Mendocino Fracture Zone. And there's a third fault here called the Cascadia Subduction Zone. So we'll talk about this soon, but this is the North American plate here. This is the Pacific plate out here. And this little sort of wedge-shaped object is what's called the Juan de Fuca plate. So the San Andreas Fault ends right here. That's the end of the San Andreas Fault. Punkt. That's, it doesn't go any farther north. And in the 1906 earthquake, it probably ruptured up to this point, and it ruptured down to about here. So virtually this entire dotted red line ruptured in a single earthquake. That's a big, big earthquake. San Francisco's there, again. The epicenter was actually fairly close to San Francisco, in that the earthquake started here and then ruptured to the south and ruptured to the north, which means that the shaking in San Francisco probably lasted a long time, but it means that the intensity of the shaking was less than if the earthquake had started here and ruptured down through San Francisco. Can anyone give me a one-word explanation for why that is? Doppler effect, yeah, great. Directivity, Doppler effect. If it ruptures down through San Francisco, starting up here, we get a lot more intense ground motions because the rupture is moving toward us. So this was a bad earthquake, but as far as magnitude 8s on the San Andreas fault go, it could have been worse, I guess is probably what I ought to say. Okay, so we've stepped out, we've seen the map of the San Andreas fault about how far it ruptured. Let's head back to the Lawson report. He mapped ground shaking. Now, this was 1906. UC Berkeley did not have a broadband digital seismic network at the time, and so we didn't have all of this data of how strong the ground was shaking, any of this numerical data of exactly the amplitude or exactly the acceleration that we felt in multiple different locations around the state. Is there a question? Yeah. So the question is that if the San Andreas fault ruptured out in the ocean, could it cause a tsunami? The answer is almost certainly not. And the reason for that is not because it's not far enough out in the ocean, but it's because the San Andreas fault is a strike-slip fault, meaning that neither block dramatically changes elevation over the course of an earthquake rupture. And what causes a tsunami is if one of the blocks moves up relative to the other block and lifts a column of water above that block up also. Right? You end up with water that's no longer at a level surface, and you create a wave that is that water trying to return to level surface. So if you just slide 2 blocks horizontally underneath a bucket of water, or underneath an ocean, you don't really change the surface, and so you don't really get a wave. It's possible to have some kind of change in elevation of the blocks of land off the coast of California, but it's not as likely as a pure strike-slip motion. Yeah. Could something like that happen on Cascadia? The Cascadia fault is this guy up here, the Cascadia subduction zone. The answer is absolutely, and we'll come back to that, but one of the ways that we know that this is a major subduction zone is because there has been recorded economic damage, so damage to buildings in Japan from what was likely an earthquake here. So yes, they can happen, they probably have happened, and we will come back to that. Any other questions? Yeah? It doesn't end. That's the end of the PowerPoint slide. It goes all the way down through Mexico. Not all the way through Mexico, but it goes down through the Mexico-California border. If the question is why did it stop rupturing there, that's a good question, but again, we have no idea. That's part of earthquake science that we don't really understand yet. Okay, back to the Lawson report. So instead of having these discrete numbers, having an idea of exactly how much the land shook during the earthquake, they didn't have these instruments. And so what they had to do was walk around and talk to people who experienced the shaking and look at the buildings, look at how much shaking probably caused the damage that was seen. Right? If we were looking at these 3 pictures, we might, we don't have any instruments in the building, so we don't know exactly how strong the ground shaking was, but we can say that there was probably stronger shaking here than, say, here. Right, because this damage is pretty extensive. This building is sort of a ghost building still standing up. This building looks seriously damaged, perhaps, but it also doesn't look like the kind of thing that if we went inside, we would certainly die. This one, we probably can't even go inside. Like, what does inside even mean when you only have 2 walls that are still standing? So they went around the entire state of California and much of Nevada and looked at the shaking, looked at looked at the damage that was done, tried to estimate the shaking. And they used a scale much like this one. This one was produced in 1931, which is why it's the modified mortality intensity scale. But they used something very much like this. Your homework assignment is going to be becoming very familiar with this scale. I don't want you to read the whole thing right now unless you're just really fast at reading. And you also are not going to need to memorize, like, intensity, what Roman numeral is that? 6. Intensity 6 is exactly these words, right? But what you should know is that 1 means that it's not felt. And it goes up to 12, which is really, really strong shaking. So again, this is not something you need to memorize, but something to have a general idea of what is a lot of shaking versus what is not a lot of shaking. So they basically went through this exercise. They see this building, and they choose one of these numbers. I'm going to give everyone a minute to read through these numbers, and then we're going to take a poll. Okay, it's been a minute, so I'm going to get started. All right, so we're going to take a poll. How many people think that this is intensity 5? Okay. How many people think that this is intensity 6? Okay, there are a few hands. Who thinks it's intensity 7? Okay, and who thinks it's intensity 8? Okay, so the fact that we all have different answers, I'm not going to go out there and say that any one of you is wrong. One of the difficult things about this is that it's purely subjective, right? You don't have an instrument that's recording exactly this amplitude, and so you know exactly what the ground shaking was like. It's subjective. You go out and look at a building, and you say, how bad does that building look? I would have chosen one of those 2, but really, honestly, any one of these 4 are possible amounts of ground shaking to have produced this kind of damage. Because we also don't know very much about the structure of this building, right? This could be a terribly built building, in which case that might be reasonable. But if you have the same person, the same group of people making these observations, then you can try and, you can sort of convince yourself that it's consistent, right? So I have another one, which I'm not going to have you all read through. I thought that it was approximately this, which is worse than before, and this picture looks kind of worse than that picture does. So they did this across the entire state, and across California, across the entire state of California and a lot of Nevada, and apparently some of Oregon too. And they developed maps like this. So this is, the color scales that I'm going to show you today are like kind of weird, I have to be honest. But in this case, it's pretty easy. Darker color means stronger shaking. So what do you notice about the distribution of shaking? Where's it concentrated? And strong shaking. So there's strong shaking along the coastline. Good. Where else? Yeah, there's like a blotch of strong shaking here. What is that? That's the Central Valley. Yeah. Why might it have shaken more in the Central Valley than here? Yes. This is a basin filled with sediment. These are mountains, so it shakes less. Interesting that there was such strong shaking all the way down here, right? That's kind of alarming. So the USGS does this kind of thing today. This is the Did You Feel It report from the Loma Prieta earthquake of 1989. So this color scale is exactly the modified mortality intensity. They don't distinguish between 10, 11, and 12. There's just X plus, which basically means you should hope that you weren't there. And so this is a community internet intensity map. So you go online to USGS, did you feel it? You log basically the things that happen to your house, and it comes up with a modified mortality intensity. So this is interesting to look at alone, but the USGS actually uses these to better refine these maps, which are instrumental intensity shake maps, which means we have an earthquake here. The earthquake was, it was X magnitude, and all of these stations recorded their individual intensities. But we can, there's all of these big gaps that are in between these stations. How do we know how much the ground shook in between the stations? And a lot of that comes from your input. You're telling USGS, this is how much shaking that I got for an earthquake that was this big and this far away. And they can learn something about the shallow structure that affects how much the earthquake shakes your building, just based on what you give it. So it's important information. It's not only fun and a community thing to go and log in what you felt and see what your intensity was, but it's also a very useful thing for the USGS. So the professor also stuck this in here. I probably shouldn't admit this. I don't have this yet, so I don't know. But apparently you can go on, if you click on the past button, so these are presumably earthquakes that are recent, from 5:34 p.m. of some day, I don't know what day. You click on the past button, it'll give you past earthquakes. What do we think this big dot is? That's probably the 1906 earthquake. Yeah, so you can click on the big, you can click on Hayward, no, it is the 1906 earthquake. It tells you what the shaking intensity is. If you click learn more with your white thumbprint, stark white thumbprint, it gives intensity 8. There's a YouTube video that looks like it's probably about how much shaking it is, so on and so forth. Okay, so this is zoomed in to the Bay Area. What did you notice about the ground shaking from this image? Where's the strongest shaking? Near the water, you say. So you're looking at this brown here? And here. Yeah, so this is exactly what he noticed, what Professor Lawson noticed. One is that the absolute strongest shaking, this very dark band, goes right along the San Andreas Fault. And the next thing that he noticed was that there also is a dark band that goes along the soft Bay mud. So I have another map that is the intensity just within San Francisco, just right in the peninsula. This is the most confusing color scale I've ever seen in my entire life. So this is strongest shaking, the brown, and then blue, and then green, and then pink, and then yellow. Okay, so let's focus on the brown. Where's the brown located? It's just right here. That's right where the San Andreas Fault is. Okay, so this is not surprising. Brown located near the San Andreas Fault. What about the next color? Blue. Where do you see most of the blue? Next to the brown, and along the water. So there's blue here, there's blue up there. So there's a geology map also. Here's the geology. Don't worry about what all the colors mean. It's similarly unintuitive. But do you notice a pattern of this color that is similar to the blue from the other page? I'm going to switch back and forth. What color tends to line up with blue? Yellow. Yeah. Yellow is man-made land. Okay, let's look at the next color. So we did brown, blue, green. What does the green tend to align with? Yeah, sort of this pink salmon color. I call it pink, but it's really not that pink. So pink is recent marine sands and alluvium. Sorry, not aluminum. Bad. Recent marine sands and alluvium. So that is not hard rock. It's sort of sandy stuff. It's softer. Good. So the green. Uh-oh. Where'd you go? Yeah, the green tends to align with that. The pink also tends to align somewhat with this other like salmonish area. But if we look at let's go back to this. If we look at the yellow, which is the weakest shaking on the map, what color does that tend to align with? All of the other weird colors, right? All of the other colors are hard rock. So they noticed, even in 1906, that your shaking is heavily dependent on how far you are from the ruptured fault and the type of land that your building is built on, right? So these are very important observations, and the Lawson report is really a turning point in earthquake science. They found out that the San Andreas Fault caused the earthquake in large part due to the shaking along, where is it? The shaking along the fault and the offset along the fault. They figured this is probably where the energy is being radiated from. They figured out a lot of things about the types of geology that you should build on, and they figured out elastic rebound theory, which is a mechanism for earthquakes to happen, which before that it was act of God, or the earth. The Greeks thought it was like hot air blowing through tunnels in the earth, much like hot air blows through tunnels in peoples and makes vibration. This is a direct quote from Plato. This is a much more feasible mechanism, though. Strain building up in the crust and strain being released. Are there any questions about the Lawson report? No? Okay, see you on, what day is today? See you Thursday.